So we learned how to interpret this, and I noted two major differences from the single regressor case. From the single regressor case, you have this difference, and adjusted R squared is now different from the original R squared. And let's review what we have done. The actual value can be decomposed into the predicted part and the residual. So you could predict the actual value this much, but the remainder is what you could not predict. We call that the residual. And actual plus equals predicted plus residual. And SER is standard error of regression, which is the standard deviation of you had. I will clarify what these two imply in the next page. So I don't like the textbook's definition, but yeah, wait a minute. And R squared is the fraction of variation in y explained by x. So that was the definition of R squared. And we now introduce the adjusted R squared. The adjusted R squared is adjusting. So what we learn, what you can mathematically show in R squared is that if you use the R squared, it always favors a model with more variables. It's kind of unfairly favorable toward regression models having more variables. So even if they are irrelevant, if you include more variables, always the R squared increase, which is not desirable. You don't want to increase. So if you include an irrelevant variable, the R squared should be stable or should not change much. So there is an additional penalty for having an additional variable. If the additional variable is not relevant enough, the adjusted R squared will drop because the irrelevant variable will drag down the overall significance or overall power of the regression model. So we will discuss in more detail. And before doing that, so SER and root mean squared error is defined in this way. The main difference, according to these authors of this textbook, is in the denominator. So residual is calculated from the results, and residual squared summation. Remember, this is the total amount of prediction errors made by your regression estimates, and you divide that by the number of degrees of freedom. The degrees of freedom is total sample size, but out of this much information, you have consumed k+1 because you have to estimate the intercept and the slopes as many as the regressors. So number of regressors and intercept is the denominator, and then of course square root makes this guy into a standard deviation. But root mean squared error, according to the authors, use only n. It does not depend on the number of regressors. So let me clarify what makes it so confusing. I forgot to put square root on everything, but you please understand. So imagine there is a square root. So in the final definition, you have to have a square root for everything. So first, the textbook and the Stata have different definitions. In the textbook, the standard error of the regression is defined in this way. In single regressor case, when you have one regressor, in our earlier chapter, we defined the standard error of the regression in this way, using the degrees of freedom n-2. Remember, n-2 is n minus 2 is coming from the number of parameters you are estimating, the intercept and the slope. So there were 2 parameters, so you have to subtract. You consume this much information before calculating the standard error of the regression. So to calculate the residuals, you need to take out this much information. And on the other hand, root mean squared error was defined in this way, using n. But in Stata root mean squared error means what SER meant in the textbook. So it is this guy. So in our result, root mean squared error is the standard error of the regression we had in the textbook. And this is calculated from this divided by this, taking square root of this guy. So square root of the sum of squares divided by degrees of freedom. Then you will get the root mean squared error, as you can see. So this is these are the conflicting definitions between the textbook and Stata. But I will respect this definition, SER, because Stata does not have SER, so it's less confusing to use SER. Otherwise, if I say root mean squared error, then there are conflicting definitions. So maybe we are going to use SER mostly rather than RMSE. So when needed, I will clarify again. So don't worry too much. Just use this chance to remind yourself of the definitions and what they meant and why. And we are going to see how they extend to multiple regressor case. So in single regressor case, standard error of regression, it was defined this way. Remember, the denominator is n-2 because there were 2 parameters, intercept and slope. 2 parameters must be estimated. So you lose degrees of freedom by 1 and number of regressors. So you had only 1 regressor, but you lose 2 because of the intercept. So 1 regressor means 1 slope plus intercept. And you can extend the idea naturally. So if you have 2 regressors, then you have to imagine two slopes and 1 intercept. So you have to subtract 3 from the number of observations. And in general, when you have k number of regressors, you have to my typo, critical typo. When I upload the slide, I will fix this typo. So when you have k regressors, you have to subtract another k minus 1. It's my typo. So that's, anyhow, it is a very natural extension of the definition. And also understanding the concept of degrees of freedom will be very useful. They are coming again later. So here they will come again in the next page. So now we will discuss the R squared. And remember, what you have to remember here is how we defined 3 sum of squared guys. So you remember these abbreviations are really annoying. So again, the abbreviations in the textbook and in Stata are different. So it's really annoying. The most annoying notation conflicts in statistics I have seen. So anyhow, TSS means total sum of squares. Total sum of squares is the total variation in the actual outcome. Total variation. And sum of squared residuals. Sum of squared residuals is the total variation in the residual which means the total amount of unexplained part. So residual is the unexplained part. So this captures the unexplained amount, and explained sum of squares. Explained sum of squares uses predicted y. So using your prediction, calculate how much variation you can have in your prediction. So this captures how much you explained the outcome by the model. And what we calculated there earlier was that the total sum of squares out of the total variation, you could explain this much explained variation. So this is a kind of percentage, and in our results we explained 42%, about 42%. So that was the ratio between them. So total variation and explained variation. Or alternatively, you may take 1 minus total variation and unexplained variation. The variation you could not explain, you could not predict. So, of course, if you could explain 42%, that means the unexplained variation is 58%, right? They are the flip sides. Always so the explained variation plus unexplained variation equals the total variation. So you can calculate their ratio as a percentage fraction. And as I said earlier, R squared, the problem in R squared is that it increases whenever you add another regressor. So it's a problem, like as I said, it increases whenever you add another regressor, even if the regressor is a bad regressor or irrelevant, whatever. Like for example, so just you write some numbers, you write random numbers in the data set and include that in your regression model. So then it should not be relevant, of course. So they are just random numbers. Still, R squared increases, so it looks like your model is better, which is misleading. So we have to adjust, we would like to adjust the R square so that it increases only when the additional regressor is relevant, good enough. So that's using this degrees of freedom. So you have to adjust this much, because you are losing when you increase more parameters, more variables, you are losing degrees of freedom on the other side. So you have to calculate, you have to penalize proportionally to the degrees of freedom. So when you compare the adjusted R square, usually it is smaller than the original R squared. So here, the original R squared is 42.64%, but after adjustment, it becomes 42.37. So it dropped a little bit, but the drop is not significant. So that means, excuse me. So in that case, the drop is little, so it means the additional variable is fine. So it does not cause much problem. And by the way, also when n is large enough, then these two guys will be more similar. Okay, that's let's stop here, and I'm going to continue. I'll see you in the next video, and I'll continue talking about this.